Okay, the last thing we talked about was the computer printout that you get that instead of using a graphing calculator, a person normally would just type in two lists of data, like in a spreadsheet. Like in this case, you can see that the variable height represents the x because we always think of y hat equals a plus bx. So b is your slope. So all the x's, b in this case, looks like it's here. Hold on, let me try to. That looks like a. So that must be x. This must be y hat. You can also match up down here in the table down here, these numbers. This number seems to match up with something called a constant. So A is a constant for all practical purposes when you look at a computer printout. And they don't always name the variable, but there's your coefficient that's next to the height. So you can see that you could actually find A and B right here from the table. You could find it if you needed to. But anyway, a person would create this printout by typing in just, in a spreadsheet. It looks like a spreadsheet. You can actually name it. You could actually name the variable x. You could name it y. Or you could actually, in this case, they've obviously named the x height. We're plugging in height and coming up with a predicted shoe size. So you can put that in a spreadsheet and just plug in the numbers. And there's always simple commands like just after you've keyed all the numbers in, you just type in a command, regression, and you have to give the name of the variables that you're using, either x comma y or height in this case, comma shoe size, because you could have other variables in your let me fix that spelling. I wasn't even looking. Shoe size. When you hit the enter button, this magic printout could appear. It doesn't give you everything in the same way your calculator does. You have to sometimes it doesn't even give you this. Sometimes you have to create this using this information here. There's a lot of information that we don't use. For instance, right now, you don't care about t-scores. Even though we're doing z-scores now, you'll see later on we'll use it, but right now, we do p-value, like the probability that z is less than 1. That's what this is, p-values. But for the line, we're not using it right now. You don't even really care about the standard deviation values right now. You might when you're doing some work by hand, but that creates the equation. There's your r squared, very important. So you got your equation, y hat a plus bx, equals a plus bx. You got your r squared. It doesn't give you r. So in order to get r, you would have to take the square root of r squared to get that. This is not used either. It's called adjusted r squared. The computer was so nice to run r squared as if you could delete some of the data that maybe seemed like influential or outlier points. So it eliminated them for you and redid the mathematics. It didn't change the equation. It just changed your r squared, but we'll never use this one. And right now, we're not going to use the standard error of the line. But at the end of the year, we're going to talk about the standard error of the line. when we talk about inferencing of regression. Right now, you need obviously you need your A and your B, your A, your B, and your R and R squared. So that's a computer printout that we'll look at some practice at some point. The new topic is residuals. Now residuals are errors. That's another word for it. It's an error. Let me draw you a picture. If you had a best fit line that was created through some well-meaning data points, and the best fit line came out to look something like this, and that's my y-hat. Every distance away from that line perpendicular is called a residual. And I told you it was an error. It's an error because it's not on the line. The y-hat is a predicted value from the line. From the scenario that we predict, we use our line, remember? These red dots that could be on the line or may not be on the line are considered, I'll point to a couple of them here. 1, 2, 3. Are they actual values? That's what we saw happen, like the diver problem. I've been diving for 1 minute. How far have I decreased the depth? I've been diving for 3 minutes. How far have I decreased the depth? I've been diving for 2.7 minutes. How far have I decreased the depth? These are things that somebody paid attention to and documented, and that became a scatter plot. But when we create our best fit line, unless R is equal to 1, which it never really is in real life, you're going to have scatter around that line. You're going to have some points above, some points below. That distance is called the error, which is a residual. We can find the distance of every residual. That one doesn't have a distance, that's R. That's a positive residual, that's a negative residual, little positive residual. And our calculator can do that. Our calculator when we go to our stat edit, that when we enter our table and we have list 1 and list 2 that we use to create our y-hat, you can create all your residuals. After you run stat calc number 8 and you create your y equals a plus bx, once you've done that, inside the calculator there are stored residuals for each of the actual values. I should not use AB. Let me just make up some numbers, 3, 5, 6, 7, and made up numbers that we saw, 8, 9, 10, 11. Once we put all that that data in and create this equation, there's residuals stored. It knows, because when you graph the line, it knows where the line is, and it knows exactly what the errors were. So you can go to L3. You go to L3, move your cursor up to L3. You hit the enter button, and down at the bottom of your screen, he will be waiting for you to kind of like keying in an equation. And here's what I want you to type in. Second, stats, number 7. You will see the word resid. When you hit enter on this number 7, out pops out residuals. I'm making these numbers up. 1.16, negative 1.4, 0.002, negative 0.87, and so forth. And it does it for every one of them. You'll have your list of residuals. If you want to see them. If you don't want to see them, you can go to your second stat plot where you created the scatter plot, and when we go to the first one, you want to see the first plot, the plot 1 that we're on, and you know how you tell it you want to do a scatter plot. Give you a little picture there, the first picture, and you choose L1 and L2. Well, you've already have the scatter plot on the screen, and you've already graphed our line, for that matter. Maybe you graphed the line, maybe you didn't, but you have already calculated it, okay? You can go back to your scatter plot. Instead of graphing L1, L2, it's kind of cool. You can just tell it to graph L1 versus the resid, which comes from, again, second stats number 7. Then when you hit zoom stat, which is number 9, remember zoom number 9, you will see the residual plot. This is to view the residual plot. Okay, so let me go back into our notes and see what I'm missing here. I didn't ask you how would I calculate a residual by hand. Well, let's go back and look at my residual plot that I started making. Since those are all my residuals, think about it. This distance here, from here, is nothing more than the actual y value that I saw right here. This is my predicted y value on the line. That difference is the length of your residual. And since it's above the line, it would be a positive residual. This actual, right here, this actual minus the predicted that would be on the line, actual, predicted, would be a negative residual because the actual was lower than the predicted value. So that takes you to your formula. Back to the formula. Observed y value minus the predicted y value. That's what your calculator did when it created that list of residuals. It actually did. Your L3 actually is the L2 minus, that was my actual, minus my Y1, that's where I pasted the equation, Y1 evaluated at list 1. That's the formula that was used to create all of those residuals. Now, when you decide to do the stat plot and look at the residual plot, I just showed you how to do it through here. You're changing the two lists we're looking at. We're looking at L1, those are my original X's. These are my Y's that I'm looking at now. These are the Y's of a new residual plot called resid. Well, the graph now, let me show you what it looks like. You're going to practice this with your calculator. You have your axis, and boom, it looks like that. And all you're going to see is that the scatter plot's now going to look like this. I'll match it up to that picture over there. Let's see. You had one that was on the line, one that was up, one that was down. I'm looking at one that was on, one that was up, one that was down. The next one was up again. The next one was down. Well, you got the picture here. And what's going on here is this line here, you don't realize it. What you're really looking at, this x-axis now is actually y hat. Because it's a value of 0. The residual is 0 for any point that is on it. Any point that's on the line, the residual is 0. This residual obviously is a positive residual. Positive residual. This point here is a negative residual. So when you graph it, all it really did was, it kind of did something like this. Let me just make something up here. If I had a best fit line, and it had some points that it went through, or made the equation, what really happened is the line turns, and it looks like this. I could actually put it on its own axis so you can see it. But that's what really happened. So let's see. This is my axis now, but the line turned. And so you see that by turning this piece here, by turning it from the way it was horizontally, you now can visually, you don't really have to think of it like this, but at least now you can see the perpendicular relationship of the residuals to y hat. That's y hat. Y hat was here. It got turned when you created the residual plot. And it's very important. It gives us a lot of information. All right, back to my notes. Some trivia, very important trivia. For the best fit line, any best fit line, when you create it, whenever you create y hat, and it has internal residuals. The sum of all the residuals is always exactly 0. Now, if you go to your calculator and you take this list 3 and you go to stat calc 1 variable stats, list 3, the number won't be exactly 0. It'll be approximately 0. It might even be something like this, negative 0.0000000052. Well, that's really 0. But see, the calculator has decimal values, and it keeps a whole bunch of decimals in the calculator forever. So it has rounding errors. The actual answer is 0 if you had every single decimal forever. Here's a definition of the residual plot. A scatter plot of the regression residuals, the ones you just created when you do the best fit line, it's graphed against the x values. That was what I just told you. Against the x values, you plotted the residuals. And the residuals were these values that went up and down above what we called was y hat. Remember, here's y hat. Residuals help us to assess how good a line is in describing the data. So you look at that residual plot. When you look at that residual plot, you can determine a lot about the original data. The big question we always ask ourselves, is the original data linear or is it nonlinear? Well, here is a very typical scatter plot. And it looks okay to me. It looks like the best fit line could magically go through and give us this nice pretty picture. But look what happens when I turn this line. Remember what I said about what exactly the residual plot was doing? I said the residual plot is actually turning it. Well, that's what's happening here. If I look at it turned, you see, you can see I have positive residuals here. I have a negative residuals here. But the calculator will do it for you. And it zooms in better, so now I can really, really, really see this positive residual, which lined up to this value right here. This negative residual zoomed in, which is most likely this one right here. I'm only counting 1, 2, 3 away, 1, 2, 3 away. And so this is a better view than looking at this one here, but it's the same idea. It's exactly the same idea. If I turn it, horizontally, you will see some similarities. It's just that this is more zoomed in than this one was. So what I want you to pay attention to in this residual plot is that there's no pattern to these residuals. They're scattered all over. No pattern, and it's a scattered. It's a mess, which is what I want. I want a mess. That means the original data that I had, that I've already written on over here, and it won't let me erase it probably. And I don't think it'll let me, maybe it will, get rid of some of it. Oh, good. The original data would be a linear fit. The original data, and that's exactly what he wrote here. The original data has a good linear fit. But look at the next one. Now, I don't have to be a genius to see that that data looks to me like a little curved pattern. If you recall the diver information we did on exercise 1, I told you that from the beginning, that I didn't like the curve that I see. That even though the r was super high and r squared was super high, I bet you if we look at the scatter plot of the residuals, we will see this pattern that looks curved. And a curved pattern, for that matter, any pattern at all on the residuals means original data is not linear. All we could say is it's not linear. Even though in this particular example, I didn't have to be a genius to see that. I could see this little curveness. But see, it didn't stop people from making a best fit line through it. I mean, I can see people trying to make a best fit line and use it. R may still be high. It doesn't matter. Remember, just because R is high doesn't mean the line's a good fit for it. It means you made it work. Now this one, the original data, it looks, look at this, the line, linear pattern looks really good, but then something happens down at the end here. What's happening is the values are getting more spread out as I go out. So what that means is it is linear, but it's less accurate after you get past the beginning. Look at this residual plot. You can see it. There's a scatter, scatter, scatter. There's no pattern. But then all of a sudden, look at, it's still scattered, but it's not very useful later on. And it's what it says. If the residual plot shows no pattern, but has an increasing or decreasing spread about the line on both sides, a linear fit can be used. But the LSRL, the least square regression line, will be less accurate for larger values of y. So I don't think there's anything else you can do with that. Okay, I talked about using your calculator. Put the data in your list, generate your scatter plot, perform the least square regression line, StatCalc 8. Go to your stat plot, change the y list to the list of the resids. This is found by second stat number 7. And then say zoom stat. And then you can see your residual plot and make a decision based on that data. So you're looking at two scatter plots. You look at your original scatter plot, you make your line, and then you make another scatter plot which shows your residual plot. Very important information. Since through all this information about residual plot, by now you already owe me the 7, 8, 9, and 10. And, well, no, I'm sorry, 7, 8. You couldn't do 7, 8, 9, 10. It was 6, 7, and 8. Explain why the linear model was not linear. I'm going to give you a hint. Besides what I told you about the curve, look at the residual plot. Look at it. And number 9 asks you to put a square around the largest residual and a triangle around the second largest residual. So create your residual plot of the diver data, then do number 9. Number 10, we did this in class. Predict how long it would take to reach the surface. If you recall, the line looked like this because as time went on this way, the depth of the water was lower because the diver was reaching the surface. The depth was decreasing. So you are to predict this value here, which we did it already. And then don't forget to explain something. You guys always do something good when it says it, predict it. But he asks you a question. In reality, do you believe that it is longer or shorter duration? That the actual value, not the predicted value, but the actual value would be higher or lower. You do the prediction. What's the exact sum of the residuals? Hello? What's the sum of that list 3? What does it all add up to? I'll give you a secret. Check it out, add up the list, and you'll see that it's very, very close to 0. Because it is supposed to be 0. Now you're going to interpret the slope. Has to do the rise over run. And so I'm going to see if you follow directions from before. So that takes you through that full page. You can continue the next part of the assignment. There's your showing you how to do the residual plot of a set of data. Now, let's go back to our original scatter plots. Don't call every data outlier just because, oh, I think it's an outlier. It might be, but it might not be. An outlier is a value that is outside the overall pattern. But unless you're going to do a box plot on the X values and the Y values and look at both of the box plots, you don't know it is. So the best thing to call it are influential observations. Because it does affect the equation of the line. That one point makes a difference. Look, even this one here. It doesn't look bad. I could probably see that the line could go through this data. It's really sloppy. Do one line and keep it there. Boom. So that line is affecting that equation a lot. As a matter of fact, he did the regression with that line, with that point in it. And he did stat calc number 4. I don't like it. We're not supposed to use it, but let's just look at what he got. I'm going to rewrite my A and B and write y hat equals a plus bx. And in his case, his A was his slope. So that becomes my B and this becomes my A. So when I write it out, y hat really is 3.38 plus 1.47x. Okay, so that's okay. It doesn't look bad. It looks like it's almost on the line. But look what happened when he removed the outlier. You can see a difference in that line. It kind of like that little point that was here was pulling the line down. Gravitational pull. And you removed it, and the line just pops up. The line just moved up. That moved up, and this part, look at that part moved up, this part moved down. This kind of shifted. You can see it in here. If you zoom in, you can see the difference of this y-intercept versus the y-intercept now. You see, it's very small. So let's see what happened. Y hat, remember, this is really my B, and this is really my A because he's using the wrong one. So y hat equals to, now it's a negative 0.1875 plus 2.20x. And you can see a big difference. I mean, I can look at the slope and see that by removing the outlier, not the outlier, the influential point, the slope increased. I can also see that the y-intercept decreased. The slope increased, got steeper, and the y-intercept decreased. All of this happened because of this influential point was pulling the line. So basically, by removing it, the whole line just shifted up. But the steepness changed, causing the y-intercept to change and the slope to change. That's very important to make that observation. And it's very important that you talk about it in terms of the context of the problem. You say slope. In our diver problem, the slope stood for the change of depth. V was the change of depth over change of time. So you have to write it in context that when I removed the influential point, the slope got steeper, which meant more depth was changed per unit of time. More depth was changed per unit of time. It meant that the diver would have been going up to the surface faster than he was originally. Remember this, I just said a minute ago. All outliers are influential. Not all influential points are outliers. So don't call them all outliers. It gets kind of, the AP test kind of frowns on that. Now that all of that, you are now responsible to finish the next page of the exercises, which is considered R2. Regression interpretation. These are all multiple choice questions based on this equation and this R squared. You have 1, 2, 3, 4, 5, 6, 7, 8 multiple choice questions. Due next time. And R3, linear square interpretation. There's 2 problems in R3. Just do the first one. You want to do the second one? That's fine, but you should be able to answer all these questions. And that takes you through everything you need to know about this lesson. And for those of you who didn't get to see me in class because I was testing PSAT, you now have all your notes. Now you can do all those exercises and get ready for a very important assessment on Thursday or Friday, whichever day you're taking it. By the way, go to the YouTube channel, subscribe. I need my 100 subscriptions. Bye.